Morning or good afternoon. In this video, we're going to start section 2.2, and that's more on functions and their graphs. And we'll check out these objectives here. Identify intervals on which functions increase, decrease, or remain constant. We'll use graphs to locate relative maxima and minima, or the peaks and valleys of the graph. We'll identify even and odd functions and how they are symmetric about the x or the y-axis. And then in the next video on 2.2, we'll work on piecewise functions and something called a function's difference quotient. And let's see, we got a graph here. It says you're probably familiar with words used to describe the graph in the figure above. Decreased. Decrease, of course, would be where the graph is going downhill. And it looks like right here in the this blue part, fuel efficiency decreased. Increase on the graph, of course, means it would be going uphill. And it looks like this entire part here, the green part, looks like the graph's going uphill the whole way. And then another couple words, minimum and maximum. And there would just be scanning across the graph and looking for the lowest the graph ever goes. That looks like it's right here. That would be minimum fuel efficiency. And then the highest point on the whole graph would be this end point here. And that would be a maximum of the graph. So let's check out the book's official definitions on increasing, decreasing, and constant parts of a graph. And there's a lot of notation in here. Just slow down, read through it, and take your time, and it just makes sense. Number one, a function is increasing on an open interval I if f of x1 is less than f of x2 whenever x1 is less than x2 for any x1 and x2 on the interval. That is quite a mouthful. But if I'm going to sketch a quick xy axis down here, and it says x1 is less than x2. So that means on the x-axis, x1 is going to be to the left of x2. Oops, back, x sub 2. And let's back, that is a 2, trust me, let's back up to the outputs. And it says that f of x1 is less than f of x2. So here on the y-axis, f of x1 is under f of x sub 2. So now that we have those in and outputs labeled on the x and y axis, this x1 would be right here, and x2 and f of x2 would be here. And if I connect the dots, you can definitely see that function is increasing, just like all this math jargon said. And we could reverse that, of course, for decreasing. X1 is less than x2. That part stays the same, so x1 is to the left of x2 on the x-axis. But now it says f of x1 is greater than f of x2. So here's f of x1. That would be this point. And then f of x2 is underneath that. So we would have to go down a little lower here. And if I connect those dots, you can see the function is decreasing. And constant would just mean it remains flat. F of x1 is equal to f of x2 for any x1 and x2 in the interval. We just have a horizontal line. So on this example here, it says state the intervals on which the function increases, decreasing, or is constant. And remember, for intervals, we're chopping up the domain, or we're chopping up the x-axis. And I notice on my graph here, there's an arrow to the right and an arrow to the left. So that means we're going to be heading toward the infinities also. So of course, this graph will start at negative infinity. And I see it starting out by decreasing. I can see this graph is going downhill until it hits the bottom of a valley, and on the x-axis that occurs at the point 0. So from negative infinity to 0, the function was increasing, and I'm going to abbreviate. So we hit the bottom of this valley here. Now we're going to go to the follow along on the graph. Oops, back that up. No. We're in the bottom of this valley. Now we're going to be on an increasing part of the graph until we hit this peak. And we've maxed out, and the x value where that peak occurred is at 2. So our next interval would be from 0 to 2. Oop, and that should be decreasing. Why did you let me write increase? Because the graph was definitely going downhill on that portion. Now we're increasing. So from 0 to 2, our function is increasing. And we're at the top of this peak. So let's see what happens. Now we're over the peak, and we're headed back down. So, and we end here at the arrow. So from this x value of 2 all the way to positive infinity, the graph is once again decreasing, going downhill. So remember, the intervals we're looking at are the x-axis being chopped up into pieces, into chunks. Let's see what's happening in B here. We got this horizontal part, and then we got, looks like half a parabola with an open circle at the bottom. So it says here 0, 2 belongs on the graph, 0, 0 does not. And that's not going to make a big deal in the notation that we do. Remember, we're looking at intervals here. So from negative infinity, our graph is constant until we hit an x value of 0. So from negative infinity to 0, we're constant. And I'm going to close this off with a parenthesis. And this, again, is the constant part of the graph. That's an NS. Now, I'm not using a bracket on there, and even though it looks like, we would use a bracket on there, this is a different type of interval. We're talking about where the function increases and decreases, and we can't just talk about a single point. I'm not worried about where I'm putting that point, should this be a bracket or a parenthesis, because at a particular point, we can't tell if we are increasing or decreasing. When we come down here and pick up on the parabola, we're going to pick up where this interval left off at 0, and the graph ends in an arrow, so we're headed off toward infinity. And this portion of the graph, we're going uphill, so we are increasing. Now the next topic, relative maxima and minima. Those are just peaks and valleys. A maxima is going to be the peak of a little hill. A minima is going to be the bottom of a valley. So our official definitions here in the box: a function value f of a is a relative max of the function f if there exists an interval containing a such that f of a is greater than all f of x's right around it. Again, f of a is greater than f of x, and a is that peak. So right here would be our relative max. Here's our f of a. It's bigger than all the other y values around it because they're all on the other side of the hill, either going back down on either side. A function value f of b is a relative min if f of b is less than all the other x's around it. So here's f of b, bottom of a valley. All the points around it are a little bit higher, so that makes f of b a relative min. Some books you'll see the word local used instead of relative, like local min or local max. And I see down there in the corner hiding is a great question. Do you use x coordinates or y coordinates when describing where functions increase, decrease, or are constant? Okay, these open intervals describe where the functions increase, decrease, or constant. Use x coordinates, not y coordinates. Remember, we're chopping up the domain, and the domain is the x-axis. Furthermore, points are not used in these descriptions. Okay, so here's our given function right here. If you had my pre-calc class before, you know that's a sine wave. It says if the graph of a function is given, we can often visually locate the numbers at which the function has a relative min or relative max. So here's our figure 217. It says the function has a relative max at. Well, let's see here. I'm going across the graph. I see this peak. It has a relative max at pi over 2. That is our x-coordinate, the member of the domain that is mapped to that peak, to that max. So the relative max is f of, and that's where we put in our domain value, f of pi over 2. And if we go up, the peak, the top of that peak on the y-axis has a height of 1. So f of pi over 2 equals 1. Or if you want to think about points, you could say the point pi over 2 comma 1 is on the graph, and also that it is a relative max. Down here it says f has a relative min at, and I look at the graph, and here's the bottom of a valley, and right above it is negative pi over 2. So that's the domain value that made that happen. Let me move this over a little bit. So the relative min is f of negative pi over 2 is equal to negative 1, because down at the bottom of this valley, that is our height on the y-axis, negative 1. So that would also again be the point, negative pi over 2, comma 1. So mins and maxes are just peaks and valleys. And what does it say here? I covered that up a little bit. Notice f, the function f does not have a relative max or min at negative pi 0 or pi. Those are the x-intercepts. You know, at negative pi, the origin and pi, we're just crossing the x-axis. Those are not mins and maxes. I think this is the last topic for this video, even and odd functions and symmetry. I'll let you read through that at your own leisure. I'll get right to the juicy stuff here in the box. The definition of an even function. If f of negative x is exactly the same as f of x for all x's in the domain, then that function's even. The right side of the equation of an even function does not change if x is replaced with negative x. A function f is an odd function if f of negative x is exactly the same as negative f of x for all x's in the domain of f. So every term on the right side of the equation of an odd function changes sign if x is replaced with negative x. Now that might be a little confusing here, but once we go through a couple problems, you'll see how just easy this is. Okay, we got to figure out, are these functions even, odd, or neither? When I look at the first one, here is f of x, and I'm just going to copy it here in blue. F of x is x to the third, x to the third minus 6x. The first thing I like to do is negate that function. I'm going to find negative f of x. And that would just be, imagine there's a set of parentheses around the original function, and we're going to distribute a negative. So now it is negative x cubed plus 6x. So I say this is option 1, the blue function. Option 2 is the red function, the original or the negative f of x. Now the last thing I want to do here is run a negative through the original function. F of negative x, I'm going to replace this x with a negative x, so now that is negative x cubed. And I'm going to replace the x attached to the 6 with also a negative x. So what is negative x to the third power? That would be negative x cubed. And then minus 6 times negative x is plus 6. So let's see, now this is f of negative x. Does this match the original function or the negated original function? Again, option 1 or option 2. Well, if I come back up here, it's equal to this one. So what we just found is f of negative x is equal to negative f of x, which by its definition means odd function. Again, to summarize, here's the original function. I negated the original function. I put a negative x through the original function and see what popped out. If I got back to the original function, I would have been even. But I didn't. I got to the negated function, which made it an odd. If it doesn't match either, then it, of course, would be neither. Let's see what happens with letter B. B, I'm just going to copy it again here in red. G of x is x to the fourth minus 2x squared. And I'm going to negate that. Negative g of x, just distribute a negative through the original function. Negative x to the fourth plus 2x squared. And now I'm going to run a negative through the original. G of negative x will be negative x to the fourth minus 2 times negative x squared. Remember, order of operations, we do parentheses and exponents first. So this is a negative x quantity to the fourth. So that's going to be a negative x multiplied by itself 3 more times. Negative times negative times negative times negative is positive x to the fourth. This negative x will be squared, and that will turn into a positive x squared times the minus 2, minus 2x squared. So this is the g of negative x, and that gets us perfectly back to the original function. And that tells us by the definition we have an even function, because g of x was equal to g of negative x. Running the negative through it changed nothing. Last one. Letter C. H of x is x squared plus 2x plus 1. I'm going to negate that function, negative h of x. I'll change all the signs by distributing a negative x, or a negative 1. Now it's a minus 2x minus 1. And I want to take the original and put a negative through it. So that is going to be negative x quantity squared plus 2 times negative x plus 1. The negative x quantity squared will be x squared. 2 times the negative x will be a minus 2x, and then plus 1. So this is our h of negative x. Is it exactly the same as the original? No, so we're not even. Is it the same as the negated version? No, because the signs are off. So it's not odd. So this would be neither. If it's not even and it's not odd, it's neither. Make sure you stick through the huddle where you do the same thing for those practice problems, because there is a shortcut, and I'll explain it after the huddle problem solutions. Now let's see what even and odd functions tell us about a graph. Blah, blah, blah. The function is even. The first thing we did was found was that the first one we did there? No. Begin with this even function, x squared minus 4. Shown down in the figure, it's even because f of negative x is the same thing as f of x. And if we look at some of the points on the graph, if we plug in a positive 3 or a negative 3 and we square it and subtract 4, we get to the same height of 5. So they're straight across from each other with the y-axis between them. Notice that we obtain the same y-coordinate whenever we evaluate a function at a value of x and its opposite, negative x. So if you plug in a 2, you get a 0. If you plug in a negative 2, you get a 0. If you plug in a 1, you get a negative 3. If you plug in a negative 1, you also get a negative 3. They will always pair up perfectly symmetrical about the y-axis. And that put the bottom of our parabola right on the y-axis. So an even function is symmetric with respect to the y-axis. Every point xy will have a counterpart negative x, comma y. All even functions have this type of symmetry, symmetric about the y-axis. So what do we have here? The graph of an even function in which f of negative x is equal to f of x is symmetric with respect to the y-axis. On the other hand, odd functions are symmetric with respect to the origin. So the graph of an odd function in which f of negative x is the same as negative f of x is symmetric about the origin, which also means it will pass through the origin. And that's a key point to remember about odd functions and their symmetry. Okay, a little thing here to wrap up with are piecewise functions. Piecewise functions are defined in different pieces. Here's our function c of t, and this is about a cell phone plan. It says the plan covers costs $20 per month that buys 60 minutes, and then additional time is 40 cents a minute. So we can represent this plan mathematically by writing total cost as a function of the number of calling minutes t. So c of t is equal to 20 if you're somewhere between 0 and 60 minutes. You got 60 minutes for your 20 bucks. After that, you start paying extra per minute. So it's 20 plus 40 cents per minute, or times the quantity, total minutes minus the 60 that we already paid for. And that's for all the minutes greater than 60. So a function that is defined by two or more equations over a specified domain is called a piecewise function. Many cell phone plans can be represented with these types of functions. And the graph of the piecewise function is shown here in the figure. So all the minutes between 0 and 60, from 0 to 60 on the x-axis, we're always at a height of 20 on the y. And then after that, we start paying more. Every additional minute is 40 cents. So we're going to use that figure from the example to find a couple of values here. Here's our c of t. It's equal to 20 if we're between 0 and 60, and then 20 plus 0.4 times t minus 60 if our minutes are over the 60. So find and interpret the following. C of 30. So this is where you look to define or find out where you are plugging your number in. Our number is 30. 30 fits in this range between 0 and 60, so we would plug 30 in for the variable t over here. But notice there is no variable t to plug our 30 into. So we would just write c of 30 is equal to 20. No matter what we put in, any number between 0 and 60, that's the number we'd replace the variable with, but there is no variable, so those all have the same output of 20. And that's the flat part of the graph. Anywhere between 0 and 60, you're on this height of 20 on the y-axis. The next one is c of 100. So 100 is greater than 60. So this 100 is going to go into the second piece of the piecewise function for this t. So that's going to be 20 plus 0.4 times the quantity, 100 minus 60. Order of operations, say work within the parentheses first. 100 minus 60 is 40. Next would be multiplication. 0.4 times 40 is 16. 20 plus 16 is 36. So that would be our cell phone bill for those minutes. Pretty expensive. 100 minutes, 36 bucks. All right, good spot to stop the video, try these practice problems, and then fire it back up. Again, after we go over checkpoint 2, I'll explain the sort of little shortcut to figure out if a function is even or odd. So let's see, in the first one we're talking intervals of increasing and decreasing. A good place to start these are find your peaks and valleys. You know, I see a peak right here. Whoa, back up. I see a peak right here, and I see a valley right here. That'll chop up our intervals of increasing and decreasing. So if I go all the way to the left, I see my arrows pointing down. We're headed over this way, so that would be negative infinity until we hit the first peak or valley, and our first peak, or our first thing is a peak here above negative 1. So from negative infinity to negative 1, our function is increasing. We're riding this left to right. We're going uphill. So from that, the interval ends at negative 1. Our next interval will start at negative 1. We're at this peak, so we'll go to the next valley, and that occurs at positive 1 on the x-axis. So from negative 1 to positive 1, we are decreasing. We're going downhill as we follow that graph left to right. Our last interval picks up where the middle one left off, so from 1, 2, and then our graph is up and off to, with an arrow at the end, off to infinity. And we are increasing because our graph is going uphill left to right. All right, even and odd stuff now. So determine if each function is even, odd, or neither. So for letter A, the first thing I would do is negate f of x, which will be minus x squared minus 6. That's a squared. And then find f of the negative x, which would be negative x quantity squared plus 6. And negative x quantity squared is x squared, and that's plus 6. And that exactly matches the original function, so that's even. We got an even. For letter B, g of x, first I will negate it. Now it is negative 7x cubed plus x. I will find g of negative x, which will be 7 times negative x cubed minus a negative x. So the negative x cubed would be negative x cubed times 7 is minus 7x cubed. The minus and negative here will turn it into a plus x. So this g of negative x matches negative g of x, which means we have an odd function. And actually, I should have wrote that up here. Odd. The last one, x to the 5th plus 1. First, negate that quantity, so that'll be negative x to the 5th minus 1. Let's see here. We'll do then h of the negative x, which will be negative x to the 5th plus 1. So the negative x to an odd power will be negative x to the 5th plus 1. Does that match the original? No. This is a positive x to the 5th. Does it match the negated? No, the signs are both off. So this is neither. And now this will lead into, I guess we could call it a little shortcut here. Notice the exponents. Here we have even exponents, even function. Odd exponents, this would be x to the 1st, odd exponent, odd function. But you got to watch out. Odd functions can be messed up by constants. Remember, a constant will be a shift up or down of the graph. All odd functions will go through the origin. If you shift an odd function up or down, anything, it's going to knock it off the origin. So odd functions are messed up by constants, and that gives us the neither. Notice this even function did not get knocked off by the constant. X squared is a parabola opening up. If I do x squared plus 6, I just move it up. It's still symmetric about the y-axis. So even functions have even exponents and constants are permitted. Odd functions must have odd exponents. Constants are not allowed. There's a shorter, easier way to find even and odd functions. The last one we have to refer back to this graph. So actually, why don't I do this? Oop, I didn't go far enough. Take it there. Letter A, C of 40. Well, 40 is in between 0 and 60. If we follow 40 up, we're going to hit the flat part of the graph. So C of 40 equals 20. Remember, the first 60 minutes we're at a flat rate of 20 bucks. That falls within the range of the flat rate. So C of 40 is 20. C of 80 is outside the range of 0 to 60, so that goes in the second piece of the piecewise function right here. So C of 80 is going to be 20 plus 0.40 times 80 minus 60. Plugging in the 80 for the t. 80 minus 60 is 20. 0.4 times 20 is 8. Oh, excuse me. Yeah. 20 plus 8 equals 28 bucks. And we could check on a graph. If we look at about 80, it would be right about here. We'd go up, hit the graph, go over, good rough estimate. We're a little bit less than 30. 28's right in there, so that's probably a good answer. Homework for this section, page 232 or 238 to 240. These handful of problems. Enjoy.